All right, so all these demos that we've done thus far, have shown these attraction and repulsion forces that must exist to make these objects move, right? And so we have these forces between electrically charged materials, and where do these forces come from, right? And oftentimes they come from not actually even touching. And we've seen this kind of force before. A force that does not actually need you to touch anything, we call a field force. And we've actually learned about field forces before. Give me some examples of some field forces. Yell them out. All right? Remember,
gravity.
Yeah, gravity, right? So they act at a distance. So we've looked at this, again, kind of to prime you guys for this future unit. We've talked about gravity as a field force. Right? Gravity acts at a distance. We've talked about magnetism a little bit. We won't get into the details of it, but magnetism, you can create a force without actually touching. And now we see that we get this electrostatic or electric field force. Just by bringing charged things, we can move them. And I guess the question I would have is, okay, so if a field exists, how do we know it exists? How do we know a field exists? Things acting kind of funny on me here. What do we know, right? If we get near a planet, how do we know it actually has gravity? If we get near a charged surface, how do we know it's charged? Well, if an object moves without being touched, we know, correct? Right? Good point, Sander. Right? So we effectively have to test it. Right? And that's really what it comes down to. We can't physically see it until we test it. Right? So we need to bring an object into the field that will react to it. And that's how we would test it. And so depending on the kind of field we have, well, we have different things we can test, right? So if we're talking about a field, a gravitational field, if we're dealing with gravity, what do we need to bring into that field in order to test it? Well, what reacts in a gravitational field? Well, we need to bring mass into the field. Any mass brought into a gravitational field would be attracted. If we're dealing with a magnetic field, we would need some kind of magnetic material or a magnet. Or a ferrous metal or a metal with iron in it. Right? And so naturally then, if we're thinking about an electric field, well, what reacts in an electric field? What do we actually need in order to react? Hopefully you're saying, well, we need to bring some kind of charge. Usually that's in the form of an electron. So we need to bring charge into the field. And when we bring some kind of charge or source of electrons into the field, we'll see some kind of interaction that occurs. And in that case, that's how we know the field must be there. Right? And for charge, we actually have a letter. We use lowercase q to represent charge. Now, to understand how electric fields work, it's really helpful to compare an electric field to a gravitational field. We know about how gravity works. Let's look at gravity as an example. We've already learned about it, so let's use this as our reference. Right? So if we have something to test gravity, it would be a mass. So let's call that m. M is what we would call a test mass. It's just brought in to test whether gravity exists, right? And if it's a test mass, it's so small that it doesn't have its own field, right? Because we know that any mass would have its own field of gravity, but we're going to bring one so small that it doesn't really affect the field we're testing. And so what we have is this large mass that we're going to call our source that's creating the field of gravity around it, right? And if I bring in a little mass, m, to test it, how will that field affect that mass? What's going to happen to m? Well, hopefully you're telling me there will be a force vector that's acting on m to pull it inward. And if I had another m that's way out over here, that force vector would also point inward, but as we learn in gravity, it's going to be smaller. As you move further away, you have less force, so I'm going to draw a smaller arrow. Well, it turns out an electric field acts in a similar way. Except instead of bringing mass into the field, we're going to bring Q into the field. Q is a test charge. And instead of a big source of mass, we're going to have a big source of charge. All right? And we'll call this our source. Right? OneNote's acting weird. And for the sake of comparison to gravity, let's make it a positive source. And let's make our test charge an electron. All right? That electron would be a negative Q, wouldn't it? And if it's a negative Q, it would be attracted with some force inward. And if I had one that was further away that was also a negative Q, it would be attracted a little bit less, right? As you get closer, that field gets stronger, similar to gravity. Now, if this was a positive test charge, well, now we would get a repelling force. So you can draw these arrows to represent the force vectors, right, away from that source. So really what we're seeing is this electric field, and we can define its field strength. Field strength, as we learned with gravity, is a vector quantity. It has both magnitude and direction, right? So we have to look at the direction component as well. And so we're going to show you just a convention here about how we draw our electric field, and we call them field lines. All right, so it's a vector quantity, and we know vectors have, I'm going to close my OneNote and open it back up here real quick. It's acting funny. We know a vector quantity has magnitude, so a length of the arrow, and it has direction. All right, that's what defines a vector quantity. I have a question. What did you say you need to use to test magnetic fields? We're not going to get into magnets, but you need some kind of iron material, right? Or a magnet itself. We call it ferrous materials. Things that have iron tend to react in a magnetic field. Not anything I'm going to test you on, but a concept that hopefully you guys are familiar with. All right, so let's draw what we call field lines. So if I have a gravitational field with a mass, well, every mass brought in is always attracted. So we would draw these arrows that act inward towards a mass to visualize the field. And these are what we call field lines. These are just drawn to visualize what would happen if you brought in a mass. All right. Now, for an electric field, it's going to depend on whether it's a positive charge or a negative charge. And something that's important when you're drawing field lines, for the field lines in an electric field, we always assume a positive test charge when drawing field direction, even though it could be an electron. So we're going to assume a positive test charge when drawing field lines. So if that's the case, a positive source would have field lines that would repel a positive test charge. Right? So they would be outward to reference that they would repel a positive test charge, whereas a negative source would attract a proton or a positive test charge. Right? So we have inward to show attraction. Right? So just showing you a little visual here. And if we want to actually quantify how strong this field is, well, we've done this before with gravity. Gravitational field strength, we've seen before. What do we use, what letter do we use for gravitational field strength? You guys remember? Hopefully, you remember, hey, we did this with Newton's universal gravitation, and it was just AG, the acceleration due to gravity. And you remember our equation? Well, AG was just big G, a constant, times the mass of the thing creating the field, the mass of the object, over the distance to the center of that object squared. And the units for the acceleration due to gravity were meters per second squared, or in this case, force per unit of mass brought into the field, newtons per kilogram. Well, then what do you think the electric field looks like? Electric field strength. Again, I'm using gravity because it's analogous. It's really similar. Well, we use another letter, a capital E. Now, these are vector quantities, so you can put the little arrow over it sometimes to reference that there's direction. And the equation for E is really similar. It's a constant, not big G, but big K. And they usually put a subscript C to reference which constant it is. A lot of constants will use K. A spring constant, remember, was K, 1/2 kx squared for spring energy. Except this K has a little C because it's Coulomb's constant. Kc is what we call Coulomb's constant. It has a value of 9 times 10 to the 9th. It's really big. Newton meters squared per Coulomb squared. And those units might give you a hint as to what the actual equation needs to be. Well, with gravity, it was big G times mass of the thing creating the field. Well, what creates an electric field? It's not mass, but it's a charge of a source. So Q is the thing creating the field, or the source charge. And any kind of charge is going to have units of coulombs. Those are the units. And d squared was the distance to the center of the gravitational source. Well, you have d squared as the distance to this charged source. distance to the source charge. And if we look at units, you can imagine what these units should be, right? If it's, for gravity, newtons per unit of mass, well, hopefully you recognize that the units for electric field would be force. It's a force field, not per mass, but per unit of charge, coulombs. So you see how analogous these two are. You have a big constant that's arbitrary, that just makes everything work. The thing creating a field, and for gravity it's mass, for electric field it's charge. And then how far away you are. And it's an inverse square law, meaning if you get further away, it gets weaker and weaker. Another thing to look at to compare the fields, let's look at these constants. Let's look at big G. Big G, if you recall, was 6.673 times 10 to the negative 11 Newton meters squared per kilogram squared. Whereas big K, Coulomb's constant, is 9 times 10 to the 9th. Right? 10 to the 6 is million, 10 to the 9 is billion. So 9 billion Newton meters squared per Coulomb squared. How do those numbers compare? Well, hopefully you recognize one's to a negative 11, one's to a positive 9. This is really small, whereas this is really big, which relates to the strength of the fields themselves. Gravity is an extremely weak force field, whereas the electric fields are really strong. Think about it. The entire Earth, think about those paper bits or the styrofoam bits or those metal bits that get picked up by that ruler when it's charged. The entire Earth is pulling those bits to the table surface. And yet you bring in a little bit of charge wiped onto a plastic ruler and they jump upward. They overcome the gravitational field to be attracted to this electric field, right? Because electric fields are really strong. All right, I'm going to set up a problem here and let you guys do a quick calculation with the electric field. All right, so here's an example problem, and then I'll throw you guys on your own here for a second. Just a quick calculation, I'll let you guys work. So what is the electric field strength (20 centimeters) away from a source charge of, and we'll make it a positive source charge, 60 nanocoulombs. So I'm going to leave you with that question here. I'm going to pause my screen capture, and I want you guys to write that down, and individually I want you to use those equations that we just did. I'm going to zoom in here so you can see your equations. There's your equation and your constant. And I'm going to pause my video and let you guys get to work. All right, guys, I'm bringing you back online here. All right, I'm bringing you back online. Let's work through this real quick. Got a couple minutes. Hopefully you got some kind of answer here, but for the sake of time, I'm just going to work through this real quick. First thing I would suggest you do is draw a quick picture. Nothing new. All right, so let's draw our source. Positive 60 nanocoulombs. Now, if we're trying to find the strength of a field, let's put our test charge out there. Well, that test charge is always a positive test charge, a positive Q. if that's the case, which way would our field arrow go? Well, hopefully you're saying, well, two positive things would repel. So I'm going to get a field, we'll label that E, that's going to point to the right. And I can label this distance 20 centimeters from here to the center. Let's identify what we have. Well, we know K is always 9 times 10 to the 9 Newton meters squared per Coulomb squared. We have a source charge, QS, equal to 60 nanocoulombs, or 60 times 10 to the 9 coulombs. Right? Remember our trick, nano is negative 9, 10 to the negative 9. The distance D is 20 centimeters, which is equal to 20 times 10 to the negative 2 centimeters. Hopefully you recognize that that would be 0.2 meters either way. And now it's just plugging in. Our field strength, E, is equal to K, Q of the source, over the distance squared, 9 times 10 to the 9 Newton meters squared per Coulomb squared, times the source charge, 60 times 10 to the negative 9 coulombs, all over the distance squared, 0.2 meters squared. And again, if you look at the units, I have meters squared, cancels with meters squared. Coulombs cancels one of those coulombs. Got newtons per coulomb. And hopefully you guys got a value for E of 13,500 newtons per coulomb. Now, it's a vector quantity, correct? So you can put that little arrow, which means we've just defined the magnitude only. Well, we need the direction. Well, what is the direction? You can't necessarily say positive, right? You have to say away from the source. And we'll do some more stuff, more examples here when I see you guys again on Wednesday. But direction's really tricky because, yeah, the way I drew it here, it's to the right, but I could have drawn that source charge anywhere around that source. And so it could have been up, could have been left, could have been at an angle, but it's always away if it's a positive source. So that's how we would define our answer, not as positive or negative, but actually as away. 60 e to the negative 9, well, it was a source of 60 nanocoulombs, and nano is 10 to the negative 9. That's what that is in our metric prefix, our metric table. So I can literally say 60 times 10 to the negative 9 coulombs as a way to convert to coulombs. You always got to get to the base unit, coulombs. Nick has a question, what else is positive other than the source charge? The test charge Q that's testing the field. The field exists whether Q is there or not. So really, if we want to find the strength of the field, it doesn't matter whether we have it Q there or not, but the direction of the field is always assuming it's a positive test charge. So since it's a positive source, its field lines are going to always be drawn going away since it's a positive source. So anything brought into that field that's a positive source, positive test charge would move away. So hopefully that answers any of those questions here. So just an example of a problem where we're basically quantifying the strength of the field. And if you look back at your notes for gravity, we did the same thing with gravity, except we said, hey, when you're on the surface of the Earth, what's the strength of the gravitational field? Oh, it's 9.8 newtons per kilogram, or meters per second squared. Hey, if you're at the space station, what is it? Oh, it's, 9.1 Newton per kilogram, or meters per second squared, right? We can quantify that, except it was always inward towards the Earth, whereas now we can go both directions based on what the source is. All right, so I'm going to stop right here. We'll revisit this on Wednesday.